Hello everyone. Today is the year 2026. A month is June. The day is the 12th, and the day of the week is Friday. And I am here today because I'm introducing a trending article from the archives. The title is Decoding Insects on a Multitask Semi-Supervised Orthoptera philosophy. The crawl is Shachivor ABS 2606 13236. It is long. I'm so excited to share this with you all today, and I have to admit, I tried talking to a grasshopper the other day, but he just told me to stop bugging him. Alright, I guess that one flew right over your heads. Anyway, let us dive right into this fascinating research paper, which deals with something called passive acoustic monitoring. You see, scientists love to put microphones in forests and fields so they can listen to the environment and figure out how healthy the habitat is, and see how biodiversity responds to environmental changes. They have gotten really good at doing this for birds and bats, but for some reason, insects have been totally left out of the party. This paper focuses specifically on a group of insects called Orthoptera, which includes our noisy little friends like crickets and grasshoppers. The big problem this paper is trying to solve is that there are basically no open-source machine learning tools that are specifically designed to identify these insect sounds in the wild. You might wonder why that is, and the answer is actually quite simple. Because collecting good audio data for bugs is incredibly difficult. Most of the audio libraries outline very clean recordings. Here you just hear one bug singing perfectly in a quiet room. But the real world is entirely different. In the real wild environment, the audio is super messy, with wind blowing and rain falling, and multiple bugs screaming over each other continuously. To fix this major issue, the brilliant researchers created a brand new system, which they decided to call Pulse. Pulse stands for Passive Acoustic Latent Space Encoder, and it is a multitask framework that combines different ways of learning, instead of just using unlabeled data, which takes forever to create. They mixed up labeled data with almost 150 gigabytes of unlabeled field recordings, which were just captured out in the wild in the United Kingdom. They used a really clever multitask learning approach, which splits the learning process into 3 different heads. There's the supervised classification head, which uses the small amount of labeled data to guess the species. Second, there's the ecological prior head, where they use a famous existing bird model called BirdNET as a teacher. They basically forced their new model to copy general ecological knowledge from BirdNET, which helps the model understand what a forest or a field sounds like in general. Third, they use self-supervised learning on the unlabeled messy audio, so the model could learn the specific acoustic profile of the local environment. When we compare this new Pulse technology to other existing technologies, the results are just mind-blowing. They compared Pulse to the state-of-the-art general Bioacoustics model called Bridge, and Pulse completely wiped the floor with it. Especially as Pulse model was way more adaptable to new environments. Because general global models often fail or may face a local domain shift with a little bit of active learning. For human experts step in to label just the most confusing audio clips. Pulse reached an area under the current score of 84%, which is incredibly high for such a difficult task. What makes this even cooler is that they did not just build a simple classification tool, but they built an interactive visualization tool for ecological discovery. I mapped out the audio embeddings into a visual space, and they found that the model actually learned ecologically meaningful structures entirely on its own. For example, the model separated the insect sounds based on the time of day. The model figured out that a morning chirp is slower than an afternoon chirp, and it grouped them accordingly without humans telling it to do so. Now let us talk about how this amazing technology can be applied to everyday life and the real world. Because I can think of at least 3 specific application examples. First, this technology could be applied to smart agricultural monitoring systems. Farmers rely heavily on understanding the insect populations in their fields, because an overpopulation of certain grasshoppers can destroy entire crops. By placing simple microphones around a farm, The pulse system could continuously monitor the exact species of insects present. If a distracted species starts to multiply rapidly, the system could alert the farmer immediately based purely on the sounds in the field, allowing for targeted pest control rather than spraying harmful chemicals everywhere. Second, this concept could be used for urban planning and city park management. City planners want to make sure that urban green spaces are actually healthy ecosystems. And listening to the wags is a great way to measure that health. By installing cheap audio loggers in public parks, city councils could automatically generate weekly biodiversity reports, showing exactly which native insects are thriving and which are disappearing. This would help them decide where to plant more native flowers, or where to reduce noise pollution, making our cities much greener and more pleasant to live in. Third, the ability to mix overlapping sounds could completely revolutionize everyday hearing aid technology. The paper mentions using non-negative least squares to separate overlapping insect songs. And this exact same mathematical approach could be adapted for human use. Imagine you're at a very noisy restaurant, where multiple people are talking at the exact same time. Just like a field full of screaming crickets. The hearing aid equipped with a similar latent space band mixing model could isolate the specific voice you want to hear, and completely tune out the overlapping background chatter. This would massively improve the quality of life for millions of people around the world. It's just so amazing to see how listening to tiny insects can lead to massive breakthroughs in artificial intelligence. The fact that they use sounds and maps to look at the exact frequencies the model is focusing on shows how transparent and powerful these deep learning models are becoming. Well, that is all the time I have for today. So keep listening to the buds, and I will see you next time.